Apparently I'm live. Excellent. And good for me. Welcome back. What a weekend, to say the least. Oh, goodness gracious. Oh, wow. I already have 18 people popped into the live chat, or a live stream or whatever. Um, that's a good thing. Just for my own sake, because I'm obviously keeping records and whatnot, just leave me a comment in the chat right there, just to give me a heads up as to who's here and who's not and whatnot. Because I see 21 people in here already, concurrent viewers, which is good. But yeah, throw me a comment in the chat. From my own records, here they go. And we'll get started in like a minute or two while people kind of get settled. You know, there they all are. Oh goodness. Yeah, the snow was interesting. The snow was very interesting. It was yesterday around noon. I'm in my driveway and I'm pouring salt. But my wife and I both know what the weather report looks like. We both know what's supposedly going to happen, because we knew the rain was going to be popping up like crazy. So it's like we put the thing down, and then when it started snowing, we were like, okay, clearly it's not the time to go outside and begin playing in the snow now, because it's like there's like barely anything. And then my daughter took a nap, and then she woke up around what, like 3ish, and then after that the snow actually did have some accumulation. So personally, I'm not a fan of going out in the snow. I'm just not. Sue me. I'm just not. My wife is. And my kids clearly are. So we made a deal, and she took them out in the few inches of snow that were out there, which I'll tell you about in a minute. And I stayed in and I cooked dinner because it was getting very close to dinner. So it all worked out great. And we got some great pictures of them in the snow. See if I can find some pictures. Hold on. I can actually do this quite easily now, because of the way that I have this thing set up right here. But yeah, we live next to a golf course. And as a result of living next to a golf course, oh, there we go. Hold on. Ah, no, go back. I'm trying to show you the pictures that we had here. Okay, good, 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 good. All right, let's see. Boom, 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 boom. Okay, let's see if I can flip this over. So, website. I could change the browser window to be that. Chapoom. There we go. So there's my daughter. There's my daughter yesterday on the right side, and then a couple of years ago on the left side, playing in that snow. And then there she is on a little makeshift sled that her grandfather made. There's my son. There's some photos of my daughter eating it for funsies, you know. And then him going down. It's just pretty awesome. And then in the backyard, it actually accumulated pretty well, you know. And then that's something else entirely. So let me get off of that. Let me get off of that and go back to here. There we go. Much better. So that's the family. Anyway, you're not here to look pictures of my kids. You're here to learn math and all that fun stuff. I don't know. I really don't know why. Anyway, so if you would, ladies and gentlemen, if you have not done so already, I'm going to need those notebooks out and open. usual setup here that I can knock out pretty easily. And of course, if you have questions, please ask them directly in the chat. Keep in mind that this is going to be an introduction to a brand new chapter. And because it's an introduction to a brand new chapter, this is going to take us in interesting directions. Kind of see how that goes. So let me kind of set myself up here. Unfortunately, I can't zoom in like I did, or like I do back at my classroom. I'm still figuring that aspect of this out. I'm sure there is a way to zoom in, but I'm not gonna mess with that right now. So today is February 1st. With September, October, November, December, January. We made it through half the school year. We did it. We did it, crew. Yeah. And this is chapter 17. As I put into the title of this video itself, it's called Sampling Distribution Models. Now for the mini speech. Up to this point in the year, we have been focusing on what feels like, to an extent, disconnected aspects. Maybe you've seen the connections that these topics have made between each other. We started this year with randomness and sampling, how to take a proper sample in experiments. And then we backtracked it to graphical displays and the introduction to the normal distribution, which was another graphical display. Then we went into linear regression. And with linear regression, kind of took us in an odd direction, but again, that information did apply to what we're doing. And then we jumped into probability, which is like, okay, a little bit of a left turn. But all of these things are connected. All of these things will play a role in what we need to do for the remainder of this AP Stats school year. See, right now we're at the beginning of February. March, April, May. The middle of May is your AP test. And this is what I've been gunning for this entire school year. The AP test is our Super Bowl. The AP test is where we basically find out whether or not we made it or not. I don't know. If I were actually awake right now, I'd have a better, more inspirational statement where little fire sparklers would be going off to the left and the right of me. But regardless, let me show you what I'm referring to. Example. Now I just need to set up this example to kind of set up what we're going to be doing a little bit. Let's say a Gallup poll states that 33% of high schoolers experience stress. Let's say that a Gallup poll states that 33% of high schoolers experience stress. Now, there's various things that you can infer and assume based on this entire statement. Number one, Gallup is a reputable polling company. You can assume that if Gallup took a poll, that they made sure to hit all of the prerequisites that would be needed to be put into place in order to collect a typical poll. You would assume that they would have selected a random assortment of people, It says just as high schoolers, so the assumption is, well, let's just go with high schoolers in the United States, high schoolers in the world. Let's just go with the United States, just for simplicity's sake. You can assume that the questions were as unbiased as possible. And that 33%, the assumption that we are going to make is that 33% is what we have referred to as a population parameter. That 33%, we can make a good assumption that it's consistent across the United States amongst all high school students. So if I were to take a poll of high school students in New Jersey, or a poll of high school students in Florida, or a poll of high school students in Wyoming, then 33% is a good assumption for a population parameter. Now, that's not necessarily what is going to happen. We've talked in the past about experimental versus theoretical probability. This is well, I don't want to say theoretical, but it's closely associated with that of a theoretical probability. We're assuming this is what is going to happen with any sample that we take. So I can label that as population parameter P equals 0.33. Now again, just for the sake of argument, notation, we've talked about notation in the past, population parameter notation versus sample statistic notation. This P is the symbol for population parameter. If it were a sample statistic, then we wouldn't use P, we would use P hat. So you'd put like a little hat on top. And that's how you would be able to distinguish between, where I'm pointing, a population parameter and a sample statistic, which we don't have a sample statistic just yet. Oh, just yet. So now here's the scenario. We know all of this information going into what we're about to do. You, let's say randomly sample. You randomly sample 45 high schoolers. So now, knowing this information of like, okay, 33% is the assumption, now you actually go out and properly conduct a poll where you randomly sample 45 high school students. What is the probability that 12 or less of them experience stress? There we go. So we go into the assumption that the population parameter is 33% based on this Gallup poll. Gallup knows what they're doing, but then you, as a high school student, are going out and you're randomly sampling 45 high school students. Okay. Well, hold on. Where's my, get my calculator here. My drawer is stuck. Come on, calculator. I need to show a couple things, and I don't have my regular calculator that is on my computer. So I'm going to use this sucker. Covered in dust. Anyway. So 45 high school students. I'm not going to write this down just yet, but let me just do a couple calculations here. 45 high school students. If we are looking at 33% of them, we assume 33% of them would experience stress. 14.85 is what we would, quote unquote, expect to happen. 14.85 is what we would expect to happen. The calculation that I just did was n times p, which is the expected value of a binomial distribution. 14.85. That's what we would expect to happen. So the question is, what is the probability that we would have 12 or less experience stress? which would be less than average. Okay. Now, there's something interesting that actually comes into play. I mentioned the binomial expectation, n times p. In order to answer this question, I'm going to have to take a little bit of a rabbit trail. I am going to have to take a little bit of a rabbit trail and write down a couple of statements. And then we'll come back to that question. I don't give you that many, but I do want to give you a star. First, as the number of trials I put A, as the number of trials increase, a binomial model approaches that of a normal model. So something very important here that's going to make a connection. We just spent these chapters dealing with probability and dealing with binomial distributions. Binomial distribution, n times p giving you the expected value, finite number of trials. One second here. Did my thing freeze? Yeah, my thing totally froze. Let me see if I can get this done again. Sorry, my camera froze right here, and I just got to get it reconnected real quick. What is going on here? Come on, silly thing, you. Am I seriously going to have these issues again? Okay. Close that. Open that back up. It should refresh. Goodness gracious. I'm going to have these issues again, aren't I? Come on, you were doing so well up to this point. Goodness gracious. It says connected, but it's clearly not. There it goes. Okay, disconnected. Something refreshed. There we go. IV cam, connected, perfect. It's coming back. There we go. There we go. Good. Okay, back to this. As a normal model, as the number of trials in a binomial model increase, you have a finite number of trials and you're looking for a certain number of successes within those trials. This is completely related to what we're about to do, because you have a certain number of trials, say 45 high school students, and you're looking for a certain number of successes, 12 or less experiencing stress. Everything in this is related to a binomial model, but what I'm about to do is relate this to a normal model using binomial formulas. Kind of. N times p we definitely needed. But as the number of trials increase, a binomial model approaches that of a normal model. The general rule of thumb comes down to this. If you have a small number of trials, and when I say a small number of trials, I mean like, 4 or 10 or some junk like that, then by all means use the binomial model that we have used in the past. But if your number of trials are increasing, I don't know, let's say like 45 or something like that, then perhaps it would be in your best interest to use that of a normal distribution. Now, how we actually do that, we'll see in a moment. In order to use a normal model for this example, and this example I'm referring to is the students experiencing stress, assumptions slash conditions must be met. Now, this is honestly going to be the bread and butter of AP statistics. Ultimately, AP statistics boils down to, I want to perform this calculation or test, what have you, hypothesis test. But in order to do so, I need to make sure these assumptions and conditions are met. Depending on the type of model that you want to use, in this case the normal, the assumptions and conditions are going to change ever so slightly. So please keep that in mind. They may change from time to time, but a lot of them will remain kind of the same. So let me talk about the conditions over here. Conditions, and then I'll do assumptions over here. Assumptions. There we go. First of all, the sample is less than 10% of the population. We've talked about this in regards to the binomial model. It's a similar condition. It's the 10% condition. Your number of trials has to be less than 10% of the population. The general idea is that if you go over 10%, then the assumed proportion or probability of success would change. That happens when you are not allowed to select repeats or duplicates from a population. You're not selecting 45 of the same person for this stress example. You're selecting 45 different people, no replacement. So each trial should be independent of the next, which I'll get to in a moment. But having your sample less than 10% of the population is one of those insurances that your trials are independent of each other. So 45 people, clearly less than the population of high school students. Next, must be a random sample. Whatever sample you end up taking must be a random sample. Now, yes, the population parameter is typically assumed, and it's Gallup, so we can assume random sample. But more importantly, the 45 students that we selected, that's what it's referring to. Not the population parameter, but the sample, which was the 45 students, must be a random sample. So that's why I had to add in that little extra thing. Typically, problems are going to include that it's a random sample. Sometimes you can infer that it's a random sample, but it depends on the context and the wording. Now, so bullet point, samples less than 10%. Bullet point must be a random sample. So, next two conditions kind of go hand in hand with each other. You must have greater than 10 expected successes, and you must have greater than 10 expected failures. There actually is a proof as to why we need more than 10 expected successes and 10 expected failures, but that proof is a bit more advanced than what you're going to be learning in AP statistics. It's again something that you would learn in a higher level statistics course. It's just one of those things for the time being where I would just be like, you got to trust me on that one. You got to have more than 10 expected successes, more than 10 expected failures. Now, if those conditions are met, there are certain assumptions we can make. Well, the sample being less than 10%, nothing within the sample indicating that there could be any shenanigans going on, more than 10 successes, more than 10 failures, mind you, expected, not actual. Then the assumption that we can make is that independence, or that we have independence of sampled values. This is one of the assumptions that we can make. If it's a random sample and we have less than 10% of the population and we have those more than 10 expected successes and expected failures, then independence is easily assumed. Sometimes within the wording of a question, they will tell you, hey, assume independence. And then you're like, good. And then finally, one assumption is that your sample size is, and I'm putting this in quotes, and I want you to put the same quotes around them, quote, large enough, end quote. This again is one of those things in statistics where the rules are fluffy. Does the distribution look normal enough? Does the scatter plot look straight enough? Is your sample size large enough? Well, is it? I don't know. Well, yeah. As long as it's a decent enough number. Depending on the textbook that you read and depending on the person that you talk to, some will say that you have to have more than 20 in your sample, or you got to have more than 35 in your sample. It's kind of iffy at that point. It's really kind of iffy. But for the most part, yeah, 45 is large enough. I'm just arguing, what would not be large enough? Well, if you didn't have more than 10 successes and more than 10 failures, perhaps your sample size would not be large enough. That's actually where people get the number 20 from. Because if you have more than 10 expected successes and more than 10 expected failures, then at a bare minimum, you'll have like 20. Actually, it says greater than, so technically, I mean, it could be like 10.1 or some junk like that. So at a bare minimum, you'd have like 20. That's generally a good rule of thumb. But for this assumption, there's no specific number stated. And here's the kicker to the whole thing. You could do a problem and you might have like 9 expected successes, and then you can still actually go ahead with the procedures. The only thing that you would have to then say in your ultimate conclusion is that, well, one of the conditions, getting 10 expected successes, was not met. We had 9, so we decided to proceed with the model with caution, or something along those lines. It's so messed up that, well, these are what we would like to hit, and if we don't hit it, then meh. But that's what statistics really comes down to. These are ideal conditions and assumptions. But if they're not met, then statisticians, they don't fudge the numbers, but they proceed with caution. It's like extrapolation. Extrapolation is not something that we like to do, but if we do it, then we do take it very cautiously with a grain of salt, and it's not necessarily something that we trust. Now, ultimately, this whole setup with conditions and assumptions, this is something that's going to set you up down the line, because you're going to be faced with AP problems much later on down the line where it's like, okay, what do I do first? Okay, well, I got to state certain hypotheses, and then step 2, you've got to state those assumptions and conditions. And when I say state those assumptions and conditions, I mean you actually have to write them out in the context of the problem. You actually have to write them out in the context of the problem. Meaning, I wouldn't just say samples less than 10% of the population for this problem. I would say 45 is less than 10% of the population of high school students. It says must be a random sample. Well, I would just say random sample stated in the problem. Greater than 10 successes and failures expected. I wouldn't just say that, I would calculate it. And I would show that calculation, or the result of that calculation. And I'll show you all of that when we actually go through the problem. Independence. Well, I would say independence of high school students experiencing stress. Again, sample size large enough. 45 is a large enough sample, is what I would say. You must state them in the context of the problem. I don't know how many times I've said the word context since the beginning of this school year. But as I've said in the past, other classes, they've been like, oh, Stark, we gotta get you a t-shirt that says context or some junk like that. You know? Hold on, I dropped something. Come here, you. There you are. Okay. Finally, I gotta get you some calculations here before we actually do this. Where's my paper? There's my paper. Come on, you. There we go. Now, I'm going to split my page a little bit just because I want to show you the distinction between these things. But if you end up doing, for a sampling distribution versus a binomial distribution, I just wanted to show you the comparison of these formulas. Now, the formulas that we are ultimately going to be using are the ones on the left, because we're dealing with a sampling distribution, a sample. A sample is something taken from the population. Mainly for binomial distributions, these are more like theoretical. Like, for example, when I was talking about my family, my parents having 4 kids. You know, assuming that my parents will have 4 kids, what is the probability that they will have 1 boy or something like that? That is a binomial question, because that's something that is, well, it's theoretical, it's more abstract. Not abstract, I shouldn't say abstract, but it's something that hasn't happened, and it's something that I'm like, well, what are the chances of this eventually happening? Whereas, in a sampling distribution, it's like that experimental probability. In a sampling distribution, you have actually gone out and collected the sample. It's experimental. And because of that, we do have slightly different things that we go along with. Now, sampling distribution. Now, for example, if we're going to be talking about proportions, like we have proportions, the mean in this case we're going to be using is p, the p that was given to us. In a binomial distribution, something that we possibly may have to use in a little bit, I'm going to show you this comparison, is n times p, which would be the number of trials times p. In this case, we're going to be assuming 33%, because that's what they told us in the Gallup poll. Standard deviation for sampling distribution would be this. It is the square root of the fraction pq over n. Whereas, in a binomial distribution, the standard deviation was the square root of npq. You can see the similarities between the formulas. Obviously with the p and the q and the square root, but again, there being the n in there. Again, there is a proof behind this, but again, that's a bit more advanced for what we're trying to do at the moment. I'm going to show you something with this later. I'm going to show you something with this, these two formulas in a little bit, and how they relate to what we're doing. Because as I gave you with that star statement, as the number of trials increase for a binomial distribution, it approaches that of a normal distribution. You'll see what I'm referring to. let's do some calculations for our problem. So now we go back to our teenage stress problem. Now, there you go. P is equal to 0.33, as we've stated in the past. And I'm going to break out my calculator in a moment because my standard deviation, I'll put mu here, there we go. My standard deviation, my sigma, is going to be equal to the square root of 0.33 times 0.67 divided by 45. Probability of success times the probability of failure divided by the number of trials. Square root around that whole thing. Easiest way to go about this, just take it piecewise. 0.33 times 0.67 divided by 45, square root of that answer. Boom. 0.0701. 0.0701. I kind of wanted to finish after 3 decimals, but it was a bunch of zeros and there was a 9 later on, so I rounded it up to 0.0701. And it's approximate, but that's what we're going to do. So now, I had mentioned that we were going to be using a normal distribution. Let me go back to this statement over here. In order to use a normal model, for this example, assumptions and conditions must be met. And we did the conditions, we did the assumptions. And that's exactly what I want to do. I want to use a normal model to calculate this problem. What is the probability in a random sample of 45 high school students that 12 or less experience stress? Well, let me write this out, and then I'm going to explain to you why I did this. Here we go. Am I going to run out of room here? Yeah, I'm going to run out of room here. I'm just going to go to a new page. I have the numbers, so it's all good. But let me write this out. Normal CDF, parentheses, small number, comma, 12 out of 45, comma, 0.33, comma, 0.0701, parentheses. In order to use a normal CDF, you need to have a lower limit and an upper limit. You need to have a mean and you need to have a standard deviation. Well, my lower and upper limit, it said 12 or less experiencing stress. Well, I did that. 12 or less experiencing stress, that's actually 12 out of 45 because, again, you are dealing with proportions. Small number could be like negative 10,000 or some junk like that. It doesn't really matter. It could be 0. I mean, technically it could be 0, but I would go a little bit farther just to be safe. A normal distribution with a mean of 0.33 and a standard deviation of 0.0701. Now, I'm just going to draw a little picture here because I think this picture would be incredibly helpful for visualizing what the heck is going on here. The assumption is that the average is 0.33. And since the standard deviation is 0.0701, I'm just going to approximate these. 0.40, 0.47, 0.54, there we go. Come on, little thing. 0.26, 0.19, 0.12. We hit our assumptions and conditions, which means we can assume a normal model. Since we are assuming a normal model, the mean right in the middle is 0.33. That's where we would expect the average to happen. If I took a sample of 45 people, I would assume an average of 0.33. If I took a sample of 45 people, I would assume a standard deviation of 0.07. There's something to be said to that in a minute, but we'll talk about that. Because of that, this is the distribution. Now I'm going to put a little title here. This is the distribution of teenagers experiencing stress from a sample of 45 students. That's my title. Long-winded, I know. So, in New Jersey, I took a sample of 45 students. In Florida, they took a sample of 45 students. In Wyoming, they took a sample of 45 students. In Washington, in Oregon, in every state in America, they took a sample of 45 students. Randomly. We selected them, let's say. Let's say every high school in America took a random sample of 45 students and asked them whether or not they experienced stress. On average, about 33% would experience stress. Some schools, well, they'd have a sample that would experience stress a lot more. And some schools would have students that experience stress a lot less. But overall, this would be the distribution of all of those theoretical samples of 45 students. If I changed the sample size, that would change the standard deviation. Let me go back a page. If I changed the sample size, right here, look where I'm pointing. If I changed the sample size, that would change the standard deviation. In fact, if I increased the sample size, the standard deviation would shrink. That should make sense. This is what we've talked about pretty much from the beginning of the year. If I increase that sample size, there's less variation from the assumed 33%. If I decrease my sample size, there's more room for inconsistency. If I decrease my sample size, I'm less consistent, more varied. It would increase my standard deviation. That's a huge thought experiment right there. I'm going to calculate this normal CDF. Normal CDF, small number, comma, 12 divided by 45. I mean, I could figure out what 12 divided by 45 is, but whatever. Comma, 0.33, comma, 0.0701. Boom. This should be approximately 0.183. Conclusion statement. Conclusion statement. There is an 18.3% chance of 12 or less out of 45 teenagers experiencing stress. There is an 18.3% chance, assuming a sample size of 45, that 12 or less students would experience stress. Now that proportion, that 12 divided by 45, what was 12 divided by 45? 12 divided by 45 is approximately 26%. If I changed the question to reflect instead of 12 or less, but if I said 26% or less, the sample size would still play a huge role. The sample size would still play an unbelievable, huge role because the sample size would change the standard deviation. And because the sample size is changing the standard deviation, that is going to affect what ends up happening to this distribution and the percent chance of those things happening. 26% approximately would be like right here. That's approximate. I mean, it's not. It's like 26.6% really, so it's a little bit beyond that. It's nuts. It's absolutely nuts. I love it so much. Now, the reason why I brought up all that stuff about the binomial distribution is because of this. And again, I wish I could zoom in on my calculator right now. I wish you could see exactly what I'm trying to type out. Let me move that up a little bit right there. That might be a little bit easier to see. There we go. Oh, close that. There we go. Bring that back. There we go. Good. So let me bring back what I just calculated. I calculated normal CDF, small number, comma, that fraction, which is a proportion, comma 0.33, which is a proportion, comma 0.07, which is a proportion. Keep in mind, this is all about proportions right here. And I'm making a big deal about that for something I'm going to give you in a few minutes. That 7%, that 0.07 represents, on average, how much a sample of 45 students would deviate from that 33%. On average, sample sizes of 45 would deviate by about 7%. And again, that standard deviation would change dependent upon the sample size. But now watch what I'm about to do here. Normal CDF, small number, comma, 12, comma, it's going to be messed up, 45 times 0.33, comma, square root of 45 times 0.33 times 0.67, parentheses. Look what I just typed in. Look very close at what I just typed in. I haven't hit enter just yet because I want to show you exactly what it is that you're looking at. This top calculation is the one that I would expect you to do. This top calculation using the proper proportions is in your best interest. But I wanted to show you the second calculation just for the sake of argument because I find it very interesting. Low number, comma, 12. That's 12 or less. Notice I'm not using 12 out of 45. I'm using it as a 12, which means I'm using it as an actual count, a count of number of people. Comma, oh, you can't see it's, there you go. It had to refocus. 45 times 0.33. Now 45 times 0.33, that is n times p. That is the binomial expected value. Which reminds me, I didn't actually calculate my expected successes and failures. I'll do that in a minute. Comma, square root of npq, that would be the binomial standard deviation. Now remember what I said, that starred statement that I made. As the number of trials increase, a binomial distribution approaches that of a normal. Now I'm still using a normal CDF here, but the mean and the standard deviation that I'm using are binomial. It doesn't get you the exact same number, because remember, the idea of a binomial, as the number of trials increase, approaches that of a normal distribution. Meaning as the number of trials increase, 45 is the number of trials here, but as the number of trials increase, then those two decimal numbers would basically converge on each other. Theoretical approaching experimental. Everything we have done in this school year basically interconnects with itself. It's insane. Just as a side note, I don't know. I mean, I talked about the assumptions and conditions, but I just wanted to very quickly just show you the expected successes and the expected failures. I'll just type them. Expected successes, and I would actually write that out. I would say there are 14.85 expected successes greater than 10. And 30.15 expected failures greater than 10. I would write that out for my assumptions and conditions, just as a side note. I'm not going to do that now just because I'll do it for the next example that we do next time, but we'll deal with that. I just wanted to share that because I thought that was cool. All right. Last thing that I want to put down for you. Actually, two last things. And then kind of I want to hype something up for next class. Um, we talked about this way earlier in the school year. But we talk about categorical versus quantitative. Again, everything in the school year has been building up to what we begin today. What we begin today is everything that we're going to be doing for the rest of the school year. I mean, not everything, but shut up. Anyway, what I just wrote down was the notation for the population mean of a sample. P hat indicates a sample. This entire chapter. What we're covering right now, the chapter title is Sampling Distribution Models. The mean of P hat is what is the population mean of the sample? Well, we assume that the population mean of the sample is the population proportion, or population parameter, the proportion P. Categorical data is stuff that you can't really take an average of. What's your favorite color? Can't take an average of it. But for our sake, for simplicity's sake, we are going to consider categorical data in the realm of mainly successes and failures. What we're looking for is the success, and what we're not looking for is the failure. And in this case, well, it's a success. And then, well, what is the standard deviation of the sample? Well, the standard deviation of the sample, as we talked about before, would be this calculation, which would change dependent upon what the sample size is. Notice, what is the standard deviation, sigma, of the sample? And then we calculate it like that. Whereas if we had quantitative data, now all of a sudden we're not dealing with proportions anymore. If we're dealing with quantitative data, we're not dealing with proportions. We're dealing with numbers that you can take an average of: shoe size, height, IQ score. So what is the average, again, of x bar? X bar being the sample. Well, it would be whatever mu is. So, the average shoe size of teenagers is like, 11 or what? I don't know. I don't know what shoe sizes are. Oh, I took a sample of 45 kids. Then I'm going to assume that my average is 11. But then the standard deviation, well, if the population standard deviation is like 2, and I took a sample of 45 kids, I can't assume that the standard deviation is going to remain a 2. I can't. So instead, it's this. The population standard deviation divided by the square root of the sample size. These formulas that I just threw at you right now, these formulas are going to come into play when you are dealing with samples. If you are dealing with they took a sample of, 52 students or 52 kids, and, they took all of their shoe sizes. Cool. All right. What is the probability that we would have a shoe size of like 11 or higher? All right, we could do that. But in order to do that, we're going to need a mean and a standard deviation. Okay, cool. Well, we assumed the mean was 11, and then the standard deviation would be the population standard deviation divided by the square root of the sample. We are going towards the realm of experimental. And with these experimental samples that we're taking, eventually this is going to lead to hypothesis testing. Right now I'm just laying the groundwork. Next time we meet on Wednesday, hopefully we'll be back in class. I assume we'll be back in class. Shut up. Assuming we're back in class, I am going to be recapping a lot of the stuff with you with examples. I'm going to be going over some, like, oh, here's an example of a sampling distribution problem where we would have to use a lot of the skills that I just introduced to you today. And then, next class is the class that I get to introduce to you. Ready? The fundamental theorem of statistics. The fundamental theorem of statistics, which, if you've been paying attention since September, it won't be that much of a surprise. It really won't be. So maybe I'm hyping it up for nothing. But yeah, that's what we're going to be doing next time. It's going to be great. For me, not for you. It's going to be great for me. Anywho, it's 8:17. Get this. My superintendent sent out this email. Hold on. Just a ridiculous, stinking email where he's just like, hey guys, you could let your kids go a little bit early if you wanted to let them go enjoy the snow. And we're like, it's gonna be rain. It's like, come on, dude. I can't find the email now. It's from oh, there it is. Hold on. The spirit of what I was trying to capture earlier was that if this turns into a legit snow day, it's okay to let your students go a few minutes early so that they may have an opportunity to play. That's literally what he said. I hope you enjoyed yesterday playing, because today sucks. Anyway, I'm going to let you guys go. I have another class to get to. I got to set that junk up. But anyway, y'all have a good morning. I'm going to sit and enjoy my coffee while I wait for my next class to start. So, Auf Wiedersehen, and I'll see you on Wednesday. Woo!